Assalamu alaikum. This is lecture 23 of data security and encryption, and in this lecture we are going to continue our discussion about cryptographic hash functions. So here are the lecture contents. As we have been discussing the hash function, and in this lecture we are going to discuss the hash function based on cyber block chaining CBC. Then there will be some hash functions implementations, and we will discuss a couple of those in this lecture. And the first one is secure hash algorithm SHA, and there are different variations of SHA such as SH1, SH2, which is referred as SH-512, and there will be some examples regarding that. And finally, the current version of SHA is SHA-3, and which will be also discussed in this lecture, and its implementation. So in recent years there has been considerable effort and some successes in developing cryptanalytic attacks on hash functions. To understand these, we need to look at the overall structure of a typical secure hash function. A typical secure hash function is represented in this diagram, and it was proposed by a scientist named Merkel, and it is the structure of most used hash function in today's technology, including the secure hash algorithms SHA. The hash function takes an input message and the proportion it to number of bits referred as y of 0 to y of L. That is the L fixed size blocks of B bits each. So if necessary, the final block is padded to B bits. The final block also includes the value of total length of the input to the hash function. The inclusion of the length makes the job for the attacker more difficult. Either the opponent must find the two messages of equal length so that the hash to the same value, or two messages of differing length that together with the length values has the same value of the hash. So two hash functions here involve the repeated use of compression function, which is referred as F. We will look in the details of F in the later slides. So it takes the two inputs, the n bit input from the previous step, called the chaining variable, and B block input. At the starting of the hashing, the chaining variable has an initial value that is specified by part of an algorithm. The final value of the chaining variable is the value of the hash for successive blocks. So hash function based on the cipher block chaining. A number of proposals have been made for hash functions which are based on cipher block chaining technique, but without using the secret key. And one of the first proposal was of the Robin, and it uses the method as described here. It divides a message into fixed size blocks and uses a symmetric encryption system such as data encryption standard to compute the hash value code known as G. So it provides an initial value from the algorithm at 0, and it computes the each value for each input using the previous hash value and the successive block of the input, and the final value of the hash function is referred as the hash code G, and it is very much similar to the CBC technique, but in this case there is no secret key. So as with any hash code, this scheme is subject to the birthday paradox attack. and if the encryption of algorithm is data encryption standard, then only 64-bit hash is produced. Because DES produces a 64-bit output, the system is vulnerable to number of attacks. And one of the common attack is meet in the middle attack. This is another version of the birthday attack used even if the opponent has access to only one message and its valid signature and cannot obtain the multiple signing. It can be shown that for some form of birthday attack will be succeed against any hash scheme involving the use of cipher block chaining without the secret key, provided that either the resulting hash code is small enough or that the larger hash code can be decomposed into independent subcode. Therefore, the attention has been directed at finding other approaches to the hashing, and many of these have also shown the other weaknesses. So in recent years, the most widely used hash functions has been the secure hash algorithm SHA. Indeed, because virtually every other widely used hash function has been found to have substantial cryptanalytic weakness. SHA was more or less the last remaining standard hash algorithm by 2005. SHA was originally designed by the National Institute of Standards and Technology NIST and published as a Federal Information Processing Standard in 1993. So when the weaknesses were discovered in a secure hash algorithm known as SHA-0, it was revised in 1995 as SHA-1, and it was based on the hash function MD4, and its design is closely related to MD4 function. So SHA-1 produces a hash value of 160 bit. However, in 2002, NIST produced a revised version of standard that defined three new versions of SHA with the hash value of 256, 384, and 512, and these are collectively known as SHA-2. These new versions have the same underlying structure and use the same types of modular arithmetic and logical binary operations. So NIST issued a revised document in 2008 which added 224-bit versions to the specifications. In 2015, NIST issued another revision which added two additional algorithms referred as SHA-512-224 and SHA-512-256. SHA-1 and SHA-2 are also specified in RFC 6234, which is essentially duplicates materials from the NIST issued document but adds the C code implementation. In 2005, NIST announced the intention to phase out the approval of SHA-1 and move to the reliance of SHA-2 by 2010. However, shortly after, a research team described an attack in which two separate messages could be found that delivered the same SHA-1 hash using 2 raised to power 69 operations for fewer than 2 raised to power 80 operations previously. Previously, it was thought that needed to find a collision with SHA-1 hash, and this result should hasten the transition to SHA-2. SHA-2, or referred as SHA-12, and the logic of SHA-12 is represented here. The algorithm takes the input a message with the maximum a length of less than 2 raised to power 128 bits and produces an output with a 512 bit message digest. The input is processed in 1 kilobit blocks referred as N blocks of 1024 bits and the length of the message is L bits. This figure shows the overall processing of the message produced as a digest, and this follows a general structure, and the processing consists of number of steps. In the first step, the message is appended with the padding bits. The message is padded so that the length is congruent to the 896 modulo 10024. Padding is always added even the message is already of the desired length. The padding consists of single 1 bit followed by the necessary 0 bits as described here. In the second step, you append the length. A block of 128 bits is appended to the message. This block is treated as unsigned 128-bit integer most significant byte first and contains the length of original message in the bits before the padding. The output of first two steps yields a message that is an integer of multiple of 1024 bits in length. This is an expanded message and it is represented by the sequence of 1024-bit blocks referred as M1, M2 up to Mn, so that the total length is expanded to the message n cross 1024 bits. Step 3 provides the initialization of hash buffer. A 512-bit buffer is used to hold the intermediate and final results of hash functions. The buffer can be represented as 8 64-bit registers named from A to H. The registers are initialized using 64-bit integers hexadecimal values. Then finally the message is processed in 128-bit blocks and it is fed to a function called f and finally produce the hash code. The heart of the algorithm is a module that consists of 80 rounds and this module is referred as f. So each round takes an input of 512-bit buffer value A, B, C, D, E, F, G, H and updates the contents of the buffer. So at input, the first round of the buffer has the value of intermediate H of I minus 1. So each round T makes the use of 64-bit value WT from W0 to W79 for 80 rounds. These words represent the first 64 bits of the fractional parts of the cube roots of the first 80 prime numbers. The output of the 18th round is added to the input to the first round h of I minus 1 to produce the h of I. The addition is done independently for each of the 8 words in the buffer with which each of the corresponding words h of I minus 1 using the addition modulo 2 raised to power 64. And after all n 1024-bit blocks have been processed, the output from the nth stage is the 512-bit message digest. The constants used in A, B, C, D, E, F, G, H values provide a randomized set of 64-bit patterns which should eliminate any irregularities in the input data. And this table shows these constants in the hexadecimal format from left to right. So this figure shows the elementary SHA-512 operations on a single round. So this will show us in more detail at the logic in each step of 80 steps of the processing of one 512-bit block. So two observations can be made about the round function. For example, if you consider the first scenario, 6 of the 8 rounds of the output round function involves simply permutation. As you can see in this example, the B, C, D, F, G, H values are used for permutations by means of rotation, and this is indicated here. If you consider the second scenario, only two output words A and E are generated by substitution based on some functions such as described here in the shaded area. The word E is a function of input variables which is combined of number of other variables. So as well the round word Wt and the constant Kt words are fed as input. So it remains to indicate that how the 64-bit values referred as W are derived from the 1024-bit message. This illustrates the mapping here. The first 16 values of words W are taken directly from the 16 words of the current block. So the first 16 steps of the processing, the value of words is equal to the corresponding word in the message block referred as M of I. For the remaining 64 steps, the value of the words consists of the circular left shift by 1 bit or of the X or of the 4 of the preceding values of the words, with two of those values subjected to shift and rotate operations. As you can see in the 16th word, the words 0, 1, 9 and 14 are used with two operations referred as shift and rotations and to perform the XOR. Similarly, the next values up to 79 are produced in the similar fashion. So this figure shows the summary of SHA-12 logic. The SHA-12 algorithm has the property that every bit of hash code is a function of every bit of the input. The complex repetition of basic function f produces the results that are well mixed. That is, it is unlikely that two messages chosen at random, even if they exhibit similar regularities, will have the same hash code. So unless there is some hidden weakness in this algorithm which is not so far been published, the difficulty of coming up with two messages having the same message digest is on the order of 2 raised to power 256 operation, while the difficulty of finding a message with the given digest on the order is 2 raised to power 512 operations. As you can see, the algorithm first divides the input to uh, consistent m blocks of the similar length, and then there will be a corresponding hash values, and for each uh, of the first 16 blocks the words are formed, and for remaining blocks the words are formed from the currently produced words. And then the algorithm initializes the working variables named from the variable a to h, and the following the main hash function is applied with the 80 runs from T0 to T79, and then there are number of transpositions and substitutions are formed using each values, and finally the algorithm computes the intermediate hash values and it returns the final hash values. So at the current time, SHA-1 has not yet been broken. That means no one has demonstrated a technique for the prediction of collisions in a practical amount of time. However, this is considered to be insecure and it has been phased out for SHA-2. And SHA-2 shares the same structure and mathematical operations than similar to the SHA-1. However, it is still used, but it is a cause of concern because it used the same structure than SHA-1. Therefore, there are chances that it can also be broken because but still it is in use because it will take years to find a suitable replacement for SHA-2. Should it be become vulnerable, NIST decided to begin with the process of developing a new hash standard, and NIST announced in 2007 a competition in SHA-3 next generation NIST hash functions, and the winning design was announced by the NIST in October 2012. The SHA-3 is the cryptographic hash function that is intended to complement SHA-2 as the approved standard in the wide range of applications in the future. So a sponge function allows both variable length input and output, making it flexible structure that can be used for a hash function fixed length output, a pseudo-random number generator, a fixed length input, and other cryptographic functions. This figure illustrates this point. The input is partitioned into number of subblocks. The message is padded to achieve a length that is uh, an integer of multiple of or bits. The resulting partitions is a sequence of blocks from P0 to Pk minus 1 with the length k multiplied by or. For uniformity, padding is always added so that if n mod or is equal to 0, a padding block of or bits is added. The actual padding algorithm is a parameter of a function. The sponge specification proposes two padding schemes. The first one is referred as simple padding and it is denoted as pad 10 steric. It appends a single bit 1 followed by the minimum number of bits 0 such that the length of the result is the multiple of the block length. The second padding scheme is referred as multi-rate padding and it is denoted as pad 10 steric 1, and it appends a single bit followed by the minimum number of bits 0 again followed by the single bit 1 such that the length of the result of the multiple of the block length. This is the simplest padding scheme such that allows to secure the use of the same function f with the different bit rates r. So this figure shows the iterated structure of sponge function. The sponge construction operates on the states variable s, which is of b, which is equal to r plus c, which is initialized to all zeros and modified at each iteration. The value of R is called the bit rate. This value is the block size used to partition the input message. The term bitrate reflects the fact that R is the number of bits processed at each iteration. The larger the value of, the greater the rate at which the message bits are processed by the sponge. The value of C is referred as the capacity. As discussion of the security implications of the capacity is beyond the scope of this lecture. The essence is the capacity is a measure of achievable complexity of the sponge construction and therefore the achievable level of the security. So a given implementation can trade the claimed security for speed by increasing the capacity C and decreasing the bit rate or accordingly or in the reverse direction. The values for the default values for the algorithm C is equal to 1024 bits and R is equal to 576 bits, and therefore our B is equal to 1600. The sponge is divided into two phases. The first phase is referred as absorbing phase and the second is referred as squeezing phase. The absorbing phase proceeds uh, in the right direction and uh, in the left side of the figure, and the squeezing phase in the right side of the figure. So for each iteration in the absorbing phase, the input block to be processed padded with the zeros to extend the length from the R bits to the B bits. Then the bitwise XOR of the extended message block and the S is formed to create the B bit input to the iteration function F. Then the output of F is the value of the S for the next iteration. So if the desired output length satisfied, then the completion of the absorption phase. The first bits of the S are returned as a sponge construction termination. Otherwise, the sponge construction enters the squeezing phase. To begin, the first bits of the S are retained as a block 0. The Then the value of S is updated with the repeated execution of F. At each iteration, the first bits of the S are retained as a block of Zi and concatenated with the previous generated blocks. The process continues through the number of iterations until we have met the desired criteria. At this point, the first bits of the concatenated blocks are returned in the vector Z. Before going into the much of the detail, this table shows the supported values of bitrate R and the capacity C. So as the table shows, the hash function security associated with the sponge construction is the function of the capacity C. So now examine the iteration function f used to process each successive block of input message. If you recall that f takes an input of 1600 bit variable s consists of or bits. Considering to the message block size followed by the capacity referred to C, the internal processing function within the F, the input state variable S is organized into 5 cross 5 cross 64 bit array. The 64-bit units are referred as lanes. For our purposes, we generally use the notation A in bracket X, comma Y, comma Z to refer the individual bit with the state array. So when we are more concerned with the operation that affect the entire lanes, we designate the 5 cross 5 matrix as L of X, Y as described in the first part of the diagram. For where each entry in the matrix L is shown as a 64-bit lane, the use of indices within the matrix is shown in the figure. Thus, the columns are labeled as X while the rows are labeled as Y, and each index is from 0 to 4. That means it will have the index of total 5 in rows and columns, and the individual bits in the lanes are labeled as from Z0 to Z63. So the function f is executed once for each input block of the message to be hashed. The function takes the input S of 1600-bit state and converts into a 5 by 5 matrix of 64-bit lanes. The matrix then passes through number of rounds from round 0 to round 24. Each round consists of 5 steps, and each step updates the state matrix by permutation and substitution. The figure states that the rounds are identical with the exception of the final step in each round. The round steps are stated as the theta step, the rho step, the pi step, and the chi step, and finally the iota step. This figure shows the reference to definitions of the theta and the chi step, and the summations show the exclusive OR functions. So this figure shows the operation function of the value of the matrix in the second column and the in the second row and the third column, referred as L2 3. Several observations are in order, and each bit in the lane is updated using the bit itself and the one bit in the same bit position from each lane in the preceding column. Thus, the update value of each bit depends on 11 bits. This provides good mixing. Also, the theta step provides good diffusion. The designers of this state that the theta step provides high level of diffusion on average, and that without theta the round function would not provide diffusions of any significance. The pi step provides the permutations, lanes that are along the same diagonal increasing in y value going from the left to right prior to the pi are arranged on the same row in the matrix and after the pi is executed. The pi step is a permutation of lanes, and the lanes move position within the 5 cross 5 matrix. The second part of the image shows the implementation of a chi step. The function operates to update each bit based on the current value and the value of the corresponding bit position in the next two lanes in the same row. So this illustrates the operation of chi function on the bits of the lane 3, 2. This is the only one-step function that is non-linear mapping. Without it, the SHA-3 round function would be linear. So as described earlier, this shows the pi function performed on the state sequence. The pi function is a permutation on the lanes. The lanes move from position within the 5 cross 5 matrix. The lanes are along the same diagonal, including in the value of y rather than in the horizontal or vertical directions. This table lists the 24 64-bit round constants. Most of the bit positions are 0 and thus do not change the corresponding bits in the matrix state L00. So if you take the commutative OR of all 24 rounds constants, only 7-bit operations are active and can affect the value of length 0, 0. Of course, from round to round, the permutation and substitution propagate the effect of the function to iota function to all of the lanes and the all of the bit position in the matrix. So it is seen that the disruption of the diffusion of the theta and chi to all lanes of the state after the single round. So this concludes today's lecture, and in this lecture we discussed the hash functions based on the cipher block chaining. There were number of restrictions on the hash functions of CBC, and in the consequent secure hash algorithms are used, and the first hash algorithms were referred as SHA-0, which was phased out, and the next version was SHA-1, which is also in the time of phasing out. The update to the SHA-1 was provided as SHA-2 with the different versions of 256, 384 and 512 bits, and finally the advanced versions of SHA algorithms is SHA-3, which is based on the sponge construction and number of iteration function f. So if you want to read more, you can study the chapter number 11 of the recommended book, or you can ask any questions. Thank you very much.